Hello, everyone. In this section, we're going to wrap up Chapter 9 by discussing the linear regression model, which we have spoken about a few times already. If you remember, it's the best fit line for a data set which shows a relationship, a linear relationship between two variables. Before we learn about the linear regression model, we need to understand a concept called the residuals, and then from there we can build on the concept of the linear regression model. The concepts in this section have fancy names, but don't let them scare you. They're actually pretty simple concepts once you get to know them. Residual is actually nothing but the difference between actual price and a predicted price. So let's get to learn about it through an example, then we'll formalize the concept. So here we're going to be looking at a table of data which is going to show us the ages and asking prices for 8 Honda Accords at a dealership in Boston, and let X be the age in years and Y be the price in thousands of dollars. And we're going to first of all take a look at the data that's given in a scatter plot. From that, we're going to decide the 4 characteristics, right? And we're going to draw what appears to be a well-fit line for that data going through these 2 points, and the equation will be right there using the techniques of our last video. So you can verify that. We won't be taking the time to do that because we want to get to the new concepts in this section. But if you just find the equation of the line that goes through those 2 points, you'll get this, right, from our 9.2 discussions. Then we'll proceed to find a prediction for the price of an 8-year-old Honda according to the model that we just saw. And then we'll find the difference between the actual price of an 8-year-old car, Honda, that we can see right here, 13,000, and what the model is predicting. And that difference will be precisely what is called the residual. So here we have plotted the scatter plot. We can see that there does seem to be a fairly strong linear relationship here, correct? The older the car, the lower the price, obviously, as you would expect, right? The R actually turns out to be negative 0.87, which indicates, a rather strong linear correlation. Let's take a look at this in StatCrunch. Okay, so here I've brought the data from the table that we had, and I've sorted the values so that, we have the youngest Honda here and the oldest one here at 12 years old. And here are the associated prices in thousands of dollars. So if you recall, if we want the linear regression line, what we do is we go to Stat, Regression, Simple Linear. Now here, we're going to go ahead and use the age variable for X and the price variable for the Y variable or the response variable. And you can leave all that alone. Now we're just going to go ahead and have it show us the fitted line plot. Now later we're going to come back and revisit this once we understand the exact definition of a residual, and we'll do some we'll pick this option as well later, residuals versus X values, but that'll be in just a few minutes. So let's go ahead and take a look at the linear regression model. So there we have it. So that's where that negative 0.87 that you saw in the lesson comes from. And here is the basic equation, right? Remember that if we replace the price with y and age with x, we'll get this equation. Y equals so instead of price, we're putting y, and instead of age, we're going to put in x, right? So let me go ahead and write the mx first. So around negative 0.9 x plus 18.42, right? That's rounded, of course. So that's basically the linear regression model for this particular situation or correlation. And notice that that's the linear correlation coefficient right there. Okay? So remember that in here we have the scatter plot, and here is the line that we estimated to be a good fit line, right? It wasn't the exact same as we saw with the linear regression model in StatCrunch. It's kind of close to it, but not exactly. Let's look at that again. Notice it was right there. So not exactly that, but close to it. All right, so here we have the exact linear regression. Let's try that again. Linear regression model, right? Remember that if we replace price with y and age with x, because age, remember, is the independent variable or the explanatory variable, and price is the response variable or dependent variable. So we end up with this model, right? Notice not that far off. So these 2 points that we had picked to draw a line through and as a best fit line was pretty good line to pick, and the choice of points was a valid one. So this again is the same data sorted, and that's where that comes from. So it's not some kind of a magic formula. It's, remember, we used these 2 points, 5, 13 from here, this one, and because 2 5-year-old cars were in the study, and one was sold for 13,000, the other for 14.2. But we used this one and this one, 9.99, and we use the techniques of the last class, which is basically find the slope, right? M equals y2 minus y1 over x2 minus x1. Once you have m, plug it back in to find the value of b, and that's where that 16.88 comes from. All right. So to discuss the 4 characteristics of the association, you can see there's definitely a linear correlation, right? The association correlation is negative, right? And the strength of it is pretty strong, right? Fairly strong association here. Also, we do not appear to have any outliers, right? Next, we are asked to find out what the model will predict an 8-year-old Honda Accord to be priced at, right? Notice that we have the model right here. We're just going to replace the X with 8, right? The age. So we end up with 10.64. So basically $10.64 thousand dollars for an 8-year-old Accord according to the model, right? Next, we were asked to find the difference between the actual price of an 8-year-old Accord from the data that we were given and the predicted price according to the model. Now, if you recall from the table, let's look at it quickly. We've reproduced it here. Notice that there was exactly one 8-year-old Honda, and it was valued at 13,000. So the difference between the actual price and the predicted price will be 13 minus 10.64 or $2,360,000. Now, notice that you can also write that that's basically 2.36 times $1,000, right? So remember what multiplying by 1,000 does? It moves the decimal 3 to the right, right? So this will probably look a lot more familiar to you, right? So instead of 2.36 thousand, we would usually say $2,360. So this difference is precisely what we call the residual. Here's the formal definition of the residual. For a given data point xy, the residual is the difference of the observed value of y and the predicted value of y. So basically, observed minus predicted. The observed is the actual value we have from our data set, right? So instead of, so one way to remember this, and so that you don't make an error in the direction, in the order of subtraction, because remember, order of subtraction is important. It's not like addition where it doesn't matter if you have a plus b or b plus a. When you're dealing with subtraction, a minus b is not the same as b minus a. So we say that subtraction is not commutative. So the order of subtraction is important. So that's why here, the easy way to remember it is, remember, O comes before what? Before P, alphabetically, right? So that's a nice mnemonic way of remembering that. So observed minus predicted, right? So notice this tilde here, not tilde, I guess we call it caret, actually. I mixed it up with this one. That's what we call tilde. That's not that. That's the caret. But we don't say y minus y caret. For obvious reasons, we actually usually just call it y minus y hat. That looks like a hat, doesn't it? Why? Because hat is so much easier to say than what? Caret, right? So we usually just say y minus y hat. So the predicted value of y at a given x value for a given input value is what we use the symbol y hat for. So in our previous example, for x equals 8, which corresponded to an 8-year-old Honda Accord, y, which is the observed price or the actual price for from our data set, was 13,000, right? The model gave us, let's take a look again, 10.64 thousand of dollars, right? So now that's going to be our y hat. So that's why the residual here will be y minus y hat, which is 13 minus 10.64, which we found on our previous page to be 2.36, right? All right. So for that particular example, this is how you would have approached it, right? And that's what the residual is. The difference between the actual value and the predicted value according to the model. In that order, right? So actual value first minus the predicted value. So take a look at this data set here. Notice that this one here, the actual values are in the blue dots, right? And of course, for a given input, the predicted value will be the point right below that on the red line, right? So notice here, for example, for this point right there, the residual will be that much, right? So you find this difference and that'll be the residual. Notice that because the observed value is more than this will be the predicted value, this would actually be a positive residual, right? So with this, right, anytime the actual value is higher than the predicted value, you're going to have a positive residual. So in this scenario, this will fall above. All these points that fall above the model are going to have positive residual. Notice here, at this point, this one would have a negative residual because the predicted value would be higher than that, right? So when you do subtract this minus that, you're actually going to get a negative value, right? So remember, when the points are above, you get a positive residual, and when the points are below, you get negative. So what happens to these points on the actual model? When the model and the actual price agree, guess what? The observed value and the predicted value will be exactly the same, and therefore the residual will be 0 for those points. Notice that if all the points lied on the line, then all the residuals would be 0, and we would have an exact linear association, right? So basically what we do when we try to find that best fit line is we find all the residuals, right? And we want to take those distances, right, and minimize the amount. That way we get the absolute best fit line, right? The only problem is, as you have seen, sometimes the values are positive, sometimes they're negative, and they could cancel each other out. That's why instead of just finding the sum of all the residuals and then finding the minimum of such values, what we do is we square them first. That makes sure that all those differentials are going to get squared and therefore become positive, so we don't run into the problem of them canceling each other out and zeroing out. So that's why we take the sum of the squared residuals first. Again, notice that if the sum of the squared residuals is 0, there's going to be an exact linear association. So if we go back to our Honda Accord model, what we could do is we could actually find this sum of squared residuals. Let's see how we would do that. So here we just list all the different ages, the corresponding prices, and then the predicted value for those ages, right? So for example, we know that for 8 we have 13 as the actual observed price, right? That's the data, what the data told us. And remember, when we plugged in 8 into this model, that gave us 10.64, right? And then all we have to do is find this difference. That's going to be the residual, and finally square it. And do the same thing for each of the data points, right? So for 7, from our table, we know that the actual result was 9.2. If we plug 7 into this model, that'll give us 11.42. Then we do the subtraction, we get this, and then we square this to get this, right? So do it for every single one of these, add all those. Here is the sum of the squared residuals. We are finally ready to formally define the linear regression model. For a group of data points, the linear regression model is the linear model with the least sum of squared residuals. Its graph is called the regression line, and its equation is called the linear regression equation, which we write in this format: y hat equals b1x plus b0, where b1 is the slope and 0b0 is the y-intercept. Of course, that's nothing other than what we're familiar with in the form of y equals mx plus b. Of course, m is the slope and 0b is the y-intercept, right? Well, here, look, that's going to be the slope. And the y-intercept, of course, will be 0, b, 0, like that. So this line that we have been finding in StatCrunch using the linear regression function is basically the best fit line for a set of data that are where a linear association exists. Okay, so this time we're going to make some predictions, but we're not going to make it using the model which we found by 2 approximate points, right? Where we picked 2 points and we figured, oh, it's going to look like pretty good from this standpoint. No, we're actually going to use the exact linear regression model to make a prediction. So we're going to use technology to find the linear regression equation. We did that already, remember? So let's go back and bring it over. Okay, so if you recall, we came up with this, right? So y equals negative 0.9x plus 18.14. Actually, I can see I need to make a correction right here. Notice I switched that. It's actually 18.42. Let's fix that first. All right, so here's we have the corrected model. I just switched these up somehow. So it's 18.42 rounded to the nearest hundredths, right? So let's go ahead and take this and move it to the other page. So here we have what is requested in step 1, which is to use technology to find the linear regression equation from what we obtained in StatCrunch. We're going to predict the value of a 10-year-old accord using this model, okay? So we have y equals negative 0.9. Remember, the 0 we don't need to put in. And x is going to be the age. So here we're going to replace that with 10 plus 18.42. So now all we have to do is go ahead and calculate that. So we carefully type in negative 0.9 times 10 plus 18.42. So we get 9.42. And remember, that's in thousands of dollars, right? So the model prediction for a 10-year-old Honda Accord price is 9.42 times $1,000, right? So basically $9,420, okay? So what is the slope of the model? Well, right there we can see is the slope negative 0.90. So we know that m is negative 0.90, which obviously means there's going to be, this is a negatively sloped line, a linear model, and if you can think about it as negative 0.90 thousand, right, over 1, and remember the units down below will be in years, right? So basically we expect the price to go down $900 per year. That's what the significance of that negative 0.9 is. When you interpret the slope as, remember, the slope is the change in y over the change in x. Now, the y's are basically the prices, right? So that's going to be in dollars, right? And down below the x's, those are years. So when you do that, the unit down there is going to be years, right? So the slope is negative $900 per year. So that means we expect the price of a Honda Accord to go down about $900 per year, or 0.9 thousand, a negative. You can put it in thousands as well, but you would then say negative 0.9 thousand dollars per year. What's the y-intercept? What does that mean in this situation? Notice from the equation right there, that's going to be your b right there. So the y-intercept is going to be 0, 18.42. Now remember, this is the age, right? So that means a brand new Honda, according to this model, right? 0-year-old Honda. That means what? Brand new Honda should be priced around that much, right? According to this model. So, and remember, that's 18.42 times 1,000, which is in dollars, right? So 18,420, right? So this is the model breaking down. Why? Because we're using a data value outside of the range of the data set that we have. So we can't have a lot of faith in this. And in fact, this is not super accurate because at the time, research showed that the price was around $21,000 for a brand new Honda Accord, even without any additional options. So again, the reason this didn't fare so well is because it was outside the range. We were extrapolating. Remember, that's called extrapolation. All right, so that's basically all there is to this problem. Next, we want to look at what's called the residual plot to help determine whether a regression line is an appropriate model. Remember, I told you we'll go back to what we did in StatCrunch. This is when we want to do that right now. Okay, so if you recall, we had already done all this work, right? We put our data values in here, and then we did the plot, right? We found the linear regression line. We also found the coefficient of, the correlation coefficient. And we always get this nice graph too if we ask it to do the graph for us, right? So here's the linear regression line we've been looking at, right? And it is the one that had the equation y equals negative 0.9x plus 18.42, right? So there is another graph associated with this, which gives us a nice indication of what we're doing as well. The best way for me to show you the new graph is to actually do a new linear regression model and then add a new piece of information to it. So we go back to simple linear regression. We'll use again age for the x variable, y for the price variable, and now we can do the fitted line plot again if we like, but mainly this time we're interested in residual versus x values. So we want to highlight that, and once we have that, we can go ahead and compute. And of course, the first two screens of this and the other one are going to be identical. So notice in the first screen we have this, right? In the second screen we have the fitted line, which is the exact same one. This is where it's going to look different from this one, because this is what's called a residual graph. So here what we're plotting are the residuals rather than the data itself. So let me show you one line here which is always on residual graphs, but StatCrunch unfortunately doesn't draw it, not that I know of at least. So what I'm going to do is I'm just going to draw it myself. So let's bring in the graphing tool. All right, so the residual zero residual line, as it's called, is usually drawn in red, so we'll stick to that. So we'll just draw a line going right through here at 0. So this is what we refer to as the zero residual line. And what we are seeing here is these points, these data points, but not the points themselves, but their residual with respect to the zero residual line, right? So we can see here we have a point with a positive residual, right? And then we have another point here with a positive residual, and at the same value we get one with a negative residual. So notice that's indicated right here. We have one with a positive residual and one with a negative residual, and you can see the residual right next to it, right? So for this one, we had a price for a 3-year-old Honda Accord, and the residual was 1.28, positive 1.28. That means the actual value or the observed value was higher than what the model predicted, right? So what you're seeing graphed here is not the price, but the residual. You see, that's why it's called the residual plot. Look at this one, see? For this other point, remember we also had a 5-year-old. Notice the age there. If I move it, I can't. So you have to just look at the screen, all right? Unfortunately, I can't hold that there and show you at the same time. So look at the age. What does it say? 5, right? Notice that we had 2 cars priced we had the prices of 2 5-year-old Honda Accords. Remember, for one of them, the residual was 0.28. That means the actual price was higher than what the model predicted. Therefore, it had a positive residual. The other one, the price was less than what the model predicted. So therefore, that one had a negative residual, right? So moving on to the right, we have a 7-year-old car here priced less than what the model would predict, right? So right there, and there we have the point right here. See, here's the 7-year-old car. What you are seeing here plotted is the residual of that particular age car, right? So the 7-year-old car, it was the actual value was much less than what the model predicted. Therefore, it's quite a bit below the residual line, right? Next, we move to an 8-year-old car, right? With a price higher, with an actual price higher than the model predicts. The model prediction is right there, right? And so therefore we expect a what? A positive residual. And that's what we have indeed right here, see? The residual is in fact shown as 1.78. So 1.78 thousand above what the model predicted, right? That was the asking price for that one. Next we have this one, right? A 9-year-old car, right? Selling just below what the model predicted, right? But not much. So we expect that residual not to be very large, right? See that? The residual is negative 0.4 thousand, right? Etc. So now you see what we mean by a residual plot, right? So what point would have fallen on the red line itself if we had a data value that actually fell on the linear regression model, right? We don't have any that does that here. Therefore, you don't see any zero residual points here either, right? Because none of the prices were exactly the same as what the model predicted, right? Therefore, because remember, if the price is exactly the same as what the model predicts, then we get the y value being exactly the same as the y hat value, right? So what is y minus y hat going to be if they're equal? Well, remember they're equal, so that's going to be 0. So notice we don't have any 0 residual data points. That is what is meant by a residual graph. Notice that if a residual graph is associated with a linear association, then you're going to get this scattered around the points, the residuals scattered around the 0 residual line in this manner, right? Notice that the spread of these points, right, the vertical spread of these points is kind of close to what the vertical spread of these points is. That's an important indication of whether we're dealing with a good linear association or not, as far as the dependability of the model goes. And also note that we don't get any kind of a real pattern here. If we get a real pattern with respect to the residual line, then that means we either are looking at a nonlinear association or no association. So this actual random scattering of the residuals right around, centered around the 0 residual line is a very good model that shows us this is a very good linear model that we're dealing with. So you want this kind of scattering around the 0 residual line. And that's basically what we're dealing with here. So this is the regular plot of the best fitted line. And this is the residual plot. Okay? Now we can summarize some of what we just said. These statements apply to a residual plot for a regression line if the plot has a pattern where the dots do not lie close to the 0 residual line. Remember, in our model, they were pretty good, close to it. Then there is either a nonlinear association between the explanatory and response variables or no association. If a dot lies much farther away from the 0 residual line than most or all the other dots, then the dot corresponds an outlier. If the outlier is neither adjusted nor removed, the regression line may not be an appropriate model. And lastly, remember that the vertical spread of the residual plot should be about the same for each value of the explanatory variable, okay? So now we want to look at what's called an influential point. The scatter plot and the regression line shown below basically are showing the relationship between the hand length and the height of 75 women. The residual plot of the observations is shown on the right. So this is the residual plot. This is the actual plot of the data, right? So notice that one point seems to lie quite a bit off in this photo graph right here, and also in the residual graph, right? Because it's also going to have a very large residual, right? So it's quite a bit above. Notice that the observed value is quite a bit above what the predicted value would be according to this model, right? So that residual, that distance, or that difference is quite large and positive, right? So that's how it's indicated over here by that point. Remember, this here is not the data point. This is the residual value, right? As are all of those dots. Now, because this point is so much further from the linear model as well as from the residual plot, we know we're looking at an outlier, right? So in order to find out whether it's what we call an influential point or not, we go ahead and remove it, right? And then do a new scatter plot and see how dramatically the scatter plot changes. Okay, so after we remove, I replicated the graph from the previous page here for simplicity, for your reference. Notice that this was removed, and then we did a new scatter plot, right, of the data, and we did a new linear regression model. Notice the linear regression model changed quite a bit. This is the original linear regression model with this data point left in the set, and this is the new regression line computed by something like StatCrunch for the set of data minus that point, right? Notice that the slope of the regression line changed pretty significantly, okay? This one had a much lower slope than this one, right? When that happens, you know that the point that you just took out was an influential point, right? Now, however, notice there was also a green dot that we were following in the previous page as well. This is our previous page. See, we kind of wanted to follow the fate of that dot as well, right? So what we did is we take that dot out as well and then calculate the new regression line and also look at the new residual plot. So we notice that the residual line, when we take this point out, is not very different at all from the residual line with that point. What does that tell us? That tells us that that point is not an influential point. So remember, the procedure is very simple. Take out the point that you are wondering about and do a new regression line. If the new regression line and the old one look significantly different, then the point that you took out was an influential point. If they don't, such as in this case, then the point that you had removed was not an influential point. All right, the last thing we're going to discuss in this lesson is what we call the coefficient of determination. Now, you already know what R is, right? R is the correlation coefficient. Now, it turns out that the square of R gives us an interesting number called the coefficient of determination. And what it gives us is the proportion of the variation in the response variable that is explained by the regression line. And also, another way of thinking about it is explained by the explanatory variable. In other words, it basically tells us how well the model does at predicting changes in the response variable according to changes in the explanatory variable. So in this example, next example, we're looking at a correlation between the temperature and relative humidity in Phoenix, Arizona on June 1st, 2014, right? So notice how there definitely seems to be a linear correlation here, right? This is just a regular scatter plot. It's not a residual plot, right? So yeah, the association seems to be negative and strong, right? So in other words, the higher the temperature, the lower the relative humidity, which makes sense, right? Because the humidity evaporates with the higher temperatures, etc. So let's go ahead and at least in certain parts, right? If you're far enough away from the ocean, right, that happens. Now let's take a look at the values of R and R squared. It turns out that in this case, R squared was around 0.90, What does that mean? That means about 90% of the variation in relative humidity is explained by the regression line. So that tells you it's actually a very, very solid model regression line, and it goes very, very far in predicting the values of the humidity level based on the values of the temperature. All right. So again, you're going to be studying all of this in more detail in the next term, but we wanted just to expose you to some of these concepts so that when you see them again in the regular statistics class, you don't feel like they're like a foreign language, right? As I said, the names are very fancy, but the concepts are not super difficult to understand, you know, once you really pay attention to the details and don't let the names get you, right? So, all right, let's go take a look at that. Pretty much wraps up the lesson. Let's take a look at a few homework problems, see if there's anything we need to look at there. All right, so for this first problem, we have a true or false type of problem, and it says for a given value for a data point, given data point xy, the residual is equal to the predicted value of y minus the observed value of y. And of course, we know that that's false. If you recall, the residual, remember how we remember that? We say O before P. So the observed value first, then minus the predicted value. So the notation we use for the observed value is y itself, and for the predicted value we use y hat. So clearly this statement here would be false. Remember, this order is very important because subtraction is not commutative. In other words, y minus y hat is not the same as y hat minus y. So be very careful with the order. The only exception, of course, occurs if the ordered pair xy happens to fall on the line, so the linear regression line, in which case the observed value and the predicted value will be the same. In other words, so if xy on the regression line, then y is the same as y hat. So in that case, y minus y hat becomes 0, and of course that's going to be the same as y hat minus y. So this is the only situation in which y minus y hat and y hat minus y will be the same. In all other instances, they're not the same. And of course in mathematics, if we're going to say something holds, it has to hold for every case. So in general, y minus y hat is not considered to be equal to y hat minus y. All right, so again, the order is extremely important. Keep that in mind. So here we have a given scatter plot for, you know, obviously linear association here. And here's the best fit line, you know, the linear regression line. Model or line as we call it, and here we are given 4 residual plots. We want to know which one is the one that corresponds to this particular scatter plot. So to do that, we need to really understand what the residual plots are showing us, and the important thing to understand is that they're not showing us data values. Remember, for a given data value, they're giving us the residual value associated with a particular x value or explanatory variable. So for example, notice that right here we have a data value that falls right on the linear regression model, right? So what is the difference between the actual observed value and the predicted value? As you've probably guessed it, no difference, because they're basically the same, because the point or the data value happens to fall on the linear regression line, right? So here you would start with a 0 residual, and remember in here we're seeing residuals, right? And notice there's only two of them which would start with a 0 residual, this one and this one, right? And it can't be this one, because this is clearly not a perfect linear association, which is what would be indicated by this residual line, because for this residual line all the residuals are 0, so therefore that means all the points would fall on the linear regression model, which would indicate a perfect or an exact linear association. So therefore we can see that it can't be this, so it must be this. Now let's see if the rest of the points make sense. Notice from there we go to a point, right, for which the predicted value is less than the observed value, right? So the observed value is larger. So we have, let me bring that back because it's going to be related to this. So we have y is greater than y hat, right? Notice the actual observed value is right there. The predicted value would fall on the line right there. It would be that y value, so which is obviously slightly less, right? So notice that when y is greater than y hat, or when the observed value is greater than the predicted value, if you just move this to the other side, you end up with y minus y hat is greater than 0. So we would want to go from a 0 residual to a positive residual, as you observe here. See? Remember, these dots are indicating the residuals. So this is the 0 line for the residuals, and that would indicate all the residuals you see up here, those are positive. The ones you see below the red line, those are the negative residuals. So anytime the data, the observed value falls above the line, we're going to get a positive residual. When it falls below, like this one, we're going to get a negative residual. Why? Because notice in that case, y, which is the observed value, is actually less than the value predicted by the model, which would be right there, right? So this one, this actual value is less than the model value, which is on the line at that point. So notice we get y minus y hat is less than 0. So this, remember, this is nothing but the residual, right? So we get a negative residual for a point like that. So for points below the linear regression line, we're going to get negative residuals, and for points on the linear regression line, we're going to get 0 residuals, right? Just like that one. And for points above the linear regression line, we're going to have the y greater than y hat, so therefore we're going to get a positive residual. So remember, this is the scenario when the observed value, or let's put it this way, the ordered pair, right, xy, which is an actual data point, is above the linear regression model, right? And this is the scenario when the ordered pair xy, or a given data point, is below the linear regression model. And of course, remember, if the point or the data point falls right on the linear regression model, we get y equals y hat. So that means y minus y hat, which is the residual, is going to be 0. So this is when xy is on the linear regression model. All right, so you can see how, again, all these points will make sense. You should sit there and study this and make sure that all the residuals correspond to each these particular data values. For each data point, there's going to be a residual value, right? And you'll see a correspondence here from each point to that. So like here, you would get a residual slightly more than above zero, right? Slightly positive. This one would be more significantly positive. This one would be a negative residual right over here. So just look for it at the same X value and you'll find the particular scenario you're dealing with on this side. All right, so that's a really good problem. It really, really helps you understand the concept of residuals and residual plots. All right, so here we're dealing with a question about the coefficient of determination. Remember, we already are familiar with the correlation coefficient, right? And that we call R, right? Now, remember that the coefficient of determination is going to be the square of R, okay? Also recall that if absolute value of R is 1, we're going to get an exact linear association, right? Now, if R is positive 1, we get a exact positive linear association, right? And if R is negative 1, we get an exact negative linear association, right? Now, if R is 0, there is no linear association. And all other R values are going to fall somewhere between, you know, -1 and 1, right? So here we have R squared equals 1. Now, if you think about it, how can R squared be 1? That can only happen if R is either 1 or R is -1, right? In other words, you're going to be looking for what? You're going to be looking for an exact linear association. So these two are clearly not exact linear associations. So this would be the one where you would want to pick. Now, sometimes people get confused. They go, but you said this is a negative exact linear association. So R is -1. Why are you picking 1? Because remember, this is not R, this is R squared. So yes, for a negative exact linear association, we need a pen there, 1 second. So for this scenario, R would be -1, but once you square both sides, right, you get R squared is 1, and the coefficient of determination is the square of R, not R itself. So imagine that we had one more graph, right? We had a choice number 4, and it was like this. So we had a positive exact linear association, right? We know that for this case, R would be 1, so R squared would also be 1. So if we had an additional 1, we would have two solutions. We would actually be able to say 3 and 4, right? So remember, as long as you have an exact linear association, you can satisfy the fact that R squared is 1. All right? And that's how we go about doing that. Okay. All right, so for this last one we're going to look at together, let's go ahead and take this data into StatCrunch and run through this one more time just to make sure you know exactly how to do this. So we're basically going to open in StatCrunch. Make sure you're logged in. If you haven't logged in, log in again. So here's the data. It brought it for us into StatCrunch perfectly. So now we're going to find the linear regression equation. So remember, we're going to go ahead and go to Stat, Regression, Simple Linear, and obviously for the x variable we just pick x, for y we pick y, and here we're going to want to choose that first option only, and there we are. So remember, usually we want to write this piece first to have it in mx plus b form, right? Write this first, so we're going to round to probably 2 places. So 1.05x plus 3.03. They went to 3 places. Listen to the instructions, right? 3 decimal places. So 1.052, 1.052, because there's a 9 after the 1, you have to round up, and 3.035, because there's a 1, you don't need to round up, you just keep the 5, and that's where these 2 numbers come from. Don't forget that it gets switched up here, right? Here they give you the constant first, and then the mx term, so make sure that you're picking the right coefficient to plug into here, right? Don't go with the same order as they have over there. So let's take a look at the scatter plot to make the determination whether it's coming close. Clearly, it does come very close to the data points, right? In fact, it's the best fit line. You're not going to find any line that comes close to all these points any better than that one. That's why it's called the best fit line, right? And therefore, yes, this is a strong linear correlation. And as you can see, the R is 0.96. So the correlation coefficient is extremely high. It's almost 1, right? Notice the R, this is R squared. This is the coefficient of determination, is also quite high, right? Which means 92% of the response variables can be explained by the linear correlation, linear regression model. So that's a very, very solid linear regression model we're looking at there. So the graph of the equation does come close to the points in the scatter plot. All right, that should pretty much do it for this chapter. And as you know, we have just one more chapter, and that's it. The term is over. So you've made it this far. Make sure you don't let yourself start falling behind on homework, and you should be okay the rest of the way. And pay attention to the email that I sent regarding needing to show work, on the problems that do require work. This particular section is kind of StatCrunch heavy, but the algebraic sections definitely require a lot of work to be shown. All right, so stay safe till our next video.